Previously on this channel.
It's not exactly performing effectively. It's done like 13,000 cycle or nearly 14,000. I did leave it on, I think, overnight. It seemed to go then back up. I suspect if there was one problem to be there in the network, it'd probably be my implementation of the back propagation.
Jace, you told me you got it working. This is exciting.
We have a working neural network, which is fantastic. I got a bit excited and I started to build out a few more different things. It actually turned out to be a very small thing. If you recall last time, what happened was the orange dots would sort of be scattered all across the graph. So if I hit play, you can see the network and you can see it's already converged. I know it might seem a bit underwhelming because it works so quickly, but yeah, it's really, really cool because like running on my laptop right now, there's this neural network and we've given it this very small sort of contrived problem, but it demonstrates that we have this, I guess, a structure that can learn because we sort of coded it all up from scratch. We know all the bits and pieces that went into it. There's no sort of hidden areas. Like we can, if we're like, oh, how does this bit work? We can sort of dive deep into that section of the math and go understand it a bit more.
So we finally got there. We have a working neural network. This is quite exciting for us. What's even more exciting is that we've managed to successfully apply theory into code that has been written from scratch. So we have a reasonably good idea as to how all of this works from end to end. Not quite in a lot of detail, but enough for us to hack something together and look further into where we don't understand. And we've got some ideas about what we want to do next, which I'll share more about at the end of the video. But if you recall from the last video, the goal of our network is to identify which dots are red, and last time it wasn't doing very well at all. The orange dots, which represent what the network thinks is red, were jumping all over the shop, even after we'd left it for a few thousand rounds. But this time you can see the orange dots converged onto the red dots quite quickly, after about 10 rounds, and at the same time the error rate was approaching 0 a lot faster. It turns out that we were missing a key component known as bias, and here's Jason to tell you more about that.
So I kind of did a bit of like, I don't know what you call it, like soul searching or whatever. I then came across a technique to introduce a bias. I don't fully understand the intricacies of what that does. It sort of encourages the network when it's going on a certain path in the learning, further proceed in that path. So therefore it sort of accelerates the learning process dramatically, as you saw. That bias was all that we had to add, and it's just a parameter to every neuron, a number, and that's used as part of the weight adjustment calculation. Point is, it worked, so it's pretty cool.
Okay, so there's a few ways we've come to understand bias so far. Firstly, there's a structural change where each neuron in the network has a bias attached to it, which you can think of as a number. Secondly, there's two process changes. So how is bias used? In the first video, we talked about the learning process as being broken up into two stages, feed forward and back propagation. The first change is in the feed forward stage. During this stage, as the network is calculating the outcome, each neuron receives values from neurons in the previous layer. If we take this output layer neuron as an example, it will receive 3 values, one from each of the hidden layer neurons, and it adds all the values together, weighted by their connection. It will then add its own bias and take that entire value as its input. The second process change occurs during backpropagation, where the network is adjusting itself before beginning another round of learning. Here the network is primarily adjusting 2 parameters, the weight values on each connection, as well as the bias values on each neuron.
I've cobbled together this UI just so we can play around with the network a bit more. Now, the key thing you notice is 2 of them. So if I add the hidden layers, and then I'm also going to adjust the network so it learns a bit faster because there's more neurons. We're going to compare these two now. So this has just one hidden layer, as this one has 5. Look at it. Yeah, you can kind of briefly, it was like lighting up in segments across the graph. And then all of a sudden, it kind of all converged very quickly. And you can see even in this little graph here, it was kind of slowly learning and then kind of suddenly dropped dramatically. So typically, if you have a more complex problem, translation or like face recognition, you might need a lot of neurons to be able to capture all these intricacies, right? There's a con of having lots of neurons, right? Because one, you need probably more data in order to train it, but you can also see that it may take longer in order for it to find, I guess, a valley where it can sort of start to properly optimize. By having this interface, it just gives us a way to sort of play around with the network a little bit more.
Now that we have this basic network up and running, we want to start looking at some more complex problems. Identifying red dots just isn't that exciting at all. And so having more than one visualization is going to be very handy when it comes to understanding how the network should be structured for a given problem and goal. Generally speaking, the more complex the data, for example if we use real images instead of red and blue dots, the more layers the network will presumably need. And from what we've read so far, there's no one-size-fits-all rule for the number of layers, learning rate, and so on that are optimal for different problems. And so having visualizations will help us with experimenting and finding a suitable network structure. Even by observing the performance of these two networks, we can already make some assumptions about which one is better. We saw two networks, one with 5 hidden layers and learning rate 0.3, the second with 1 hidden layer and learning rate 0.003. In the first few learning rounds, we saw the first network struggle to identify red. There was a noticeable cluster of orange dots hovering around the blue. But does that mean it's less effective? Well, it depends. If our goal is to identify the red dots as fast as possible, then the second network is likely to win. If our goal is to be accurate, then the first one might be more suitable. Because even though it struggled for a bit, once it got the hang of what is red, we saw its error rate drop dramatically below the second one, coinciding with the orange dots converging on the red.
Originally, I was very interested in image processing. Eventually, I got to a point I was looking at this problem domain where when you take a photo of someone, you can get this undesirable effect called the red eye effect. I was looking at, okay, how can you solve this problem? So I built some image processing tools and things to correct it. They weren't always the best. This is like 10 years ago now. If only there was a way where we can automatically find a person's eyes, first off, and then some way of generating what should be there instead. Now that we have a functioning basic neural net, this is like the very start of our very first milestone. And now the journey is like, let's try and apply it to something useful. It's really exciting what we can do next.
That's right, we're leveling up here slowly but surely, and we need to decide what problem we want to solve next. The main one we've discussed is the red eye effect. I'm sure most of you would know when you take a photo with flash, there's always a chance that your pupil will show up red. Anyway, we'll decide and pick it up in the next video. If you have any suggestions, feel free to let us know. Dear Dixon, you've been invited to blah blah blah, blah blah blah. If you like this content, please subscribe.